continue for maybe 20 minutes on integrable circuits. Again, I remind you the main point of my lecture basically is to show you that one can use simple diagrammatics to calculate things for discrete canonical systems like quantum circuits. What we have showed yesterday at the end of the lecture was commutativity of time evolution of a G-quark Yang-Baxter integrable circuit with the Solvable transfer matrix. So at the end I want to sketch the proof, but I hope for those who paid attention it was clear. In the fundamental relation behind this proof, I will repeat it again on the board, the Yang-Baxter equation. In my notation, this is an equation which connects two diamonds to a box. And this box is a quantum gate, and this quantum gate can be pulled through. And the price for doing that, there is a very simple price for doing that, which is exchange of these two spectral parameters. So the difference of these two spectral parameters is precisely the time step. So remember, lambda plus minus was some lambda plus minus tau of 2. So the difference of these two spectral parameters is precisely the time step. So there has to be some compatibility, which is related to, in physical terms, the momentum conservation. But here we don't care about momentum. There is no momentum, but formally it's like momentum conservation. And that means that's basically what's behind all these nice tricks that one can use in integrability. This is a very simple fundamental relation, right? And again, let me denote the wires. So 1 and 2 will be physical space, and maybe I will put here 8 rather than 3 in order to stress that this is not zero space. So this is, let's say, A prime. We can always assign directions to everything, right? So directions will be bottom up as time and right to left as space. But never mind, you can always revert these things because everything is unitary, but that's how things work. And now that the second thing I want to show is commutativity of this transfer matrix. So another claim is this transfer matrix commutes with itself for arbitrary values of spectral parameters. So again, that's a very simple consequence of very same relation. The only thing you have to do with this relation now is to turn it upside, to turn it from 90 degrees. So what I will have to do, I'll be very, sorry, I'll be a bit sketchy here, but I hope that will be enough. So what we do now here is to, let me display a product. What does it mean to multiply two transfer matrices, right? Multiplying two transfer matrices, for me is, for us now who are used to calculated diagrams, right? It's just basically a stack of two MPOs, right? If each transfer matrix is an MPO, let me write 3 periods, and then we are done. And then this means that this is periodic boundary condition, so this is one transfer matrix. It's an operator, right? This is in, this is out, this is row, this is column for big matrix. So this is, sorry, this is, this will be one of them. This is the second one, right? Because I will put the other one below. So this is the second one, which is T of lambda. So I have to put lambda plus, lambda minus, lambda plus, lambda minus, lambda plus, lambda minus, and so on. And then the second one will be exactly the same, but here I put mu plus mu minus. Right? So again, the notation is the same. U plus minus means U plus minus tau. So the only important thing is that the difference of two spectral parameters in each pair of sides is precisely the time step. So this is the product, right? And now we want to show that this product is equal to the product when we do the you do the swap. Yeah.
Could you remind me about what is this line that gets bent downwards?
This line.
Yes.
This line means that you have to connect this point to this point, which means it's periodic long distribution. Everything is because it's a trace, right? Remember, yeah. I mean, this is a trace. I'm not it was already there yesterday, but that's yeah. And then what I said is that I have to just use this relation, but tilted. And if you tilt this relation, and then you put here lambda and u, then here instead of tau you have lambda minus u, right? So let me write this relation. And what is important is that this guy gets tilted. It's not the same. This guy, when it's tilted by 90 degrees, it's not exactly the same because remember this guy was a sum of I mean this thing again. I remind you was a sum of this plus I tau this. So if you tilt this, it's not exactly the same because this becomes different. This is identity, but if you tilt it, it becomes a projector.
But we also had a trace in the T operator, right? So
sorry, say again.
in the transfer matrix, we had the trace.
We have the trace, yes. The trace is still there. No, but in these formulas there is no trace. These formulas have all open bias because you have to apply them somewhere in the bulk of this diagram. No, traces are at the end. But you have to be able to invent this formula. So there are two things I will now use. First, I will tilt this formula upside down, but then it means I will do it. I will take this guy, but now I will not write tau here. I will write mu minus lambda, and also, and then here I will write whatever. No, I might do a Z2 mistake. It might be the other way around. I'm not able to clarify this quickly, but it's not important. I mean, of course it's important, but it's not fundamental to have it. Sorry, this is yeah, this is the problem. So now it should change. So if it's not like that, then it's not. But exactly here it is. Right? So now this is, but the content of this relation is exactly the flip of this relation. Okay, so and then the other relation is that the other relation I need is if I put two R matrices, these are R matrices, these squares, right? And these are well, yeah, these are basically R check matrices, but these are gates, right? But if you multiply these two gates like this with a negative, so this is tau, this is minus tau. If you multiply like this is unitarity, right? This is just unitarity, which means this is just this, right? This is just u diagonal is equal to nothing else. And this is again Young-Baxter. So these two things I will need to transform this product to another product. But sorry now for being a bit sloppy because I want to start discussing chaotic circuits at least in the middle of today's lecture. So I will be on the sketch here. So I will just put the slides a bit longer. Now I just do stuff like here, like erasing. Right? So what I will do now first, I will indent this. I will indent this, which means I will just put here one gate and here another gate. Like this, okay? And here I will put, this is lambda mu. Okay, I mean, it is one lambda mu.
Ну вот сейчас, почему он там, что означает то, что...
So if I want to suppose this is correct, now lambda is in the top, this should be mu minus lambda. And this should be lambda minus mu. Okay? Yeah, it's okay. Please ask if there is anything wrong. So now I didn't do anything, right? I just invented identity. I just invented identity as through Utecker, but of course this is, maybe I should put errors here to denote that this was tilted, this was flipped again. But now I will use Young-Baxter from this T2 to transform it to this. Okay? So what I mean now is if I use it once, I can erase it like that. I push this guy inside, and here I swapped. Remember what happened by using Young-Baxter, I swapped lambda mu. So now mu is on top. Here was mu minus, so it's mu minus, mu plus. lambdas. And here it is the same thing, right? It was mu minus lambda. Then I push it right to left. I push it again and again and again. Each time I push it, I swap lambda and mu. So when I push it to the very end, I will push it to the very end, then here. Then I still have mu minus lambda. Now I will erase it here. But then I have to change, then I have to swap mu's and lambdas. That's the only effect of this thing, swapping mu's and lambdas. We're almost done. Now we have the same train of products of R matrices or Lax matrices if you want. That is called Lax matrices, these blocks. I have a product of these operators, but with exchange lambda and mu. The only thing is that I have to get rid of these guys now, the boundaries. But remember, these are periodic boundaries. So I can also think of this as a neighbor of this guy. So they get manipulated by the very same identity they got created. Okay? So I can erase this guy. Identity, which means sorry for this derivation, right? But at the end of the day, what I got is T of mu, T of lambda. So now T of mu is first and T of lambda is, sorry, T of, and what happened here? I have to exchange, I forgot to exchange, right? I mean, here, when I pull these guys through, I have to exchange this guy on top below. This became lambda now, right? And these are, okay, lambda, 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 mu. So the first is lambda, and the second is mu. Okay. So now, the end of this calculation is the proof that T of lambda and T of mu commute. And any lambda. Okay, nice.
I have a question.
Yeah.
So first of all, there's no problem in connecting virtual, like I guess I was thinking of the horizontal and virtual indices. There's no problem in connecting this to like physical indices.
Connecting this vertical to.
I mean, I don't know, like the T's act on the, like physically act on the real
Yeah.
number space, and then but you're just connecting them. I don't know, at least I on the left, you're connecting them to virtual indices. So it's never a problem to work like down one. Yeah, the one in the middle, let's say.
One,
Yeah.
these vertical indices, okay? These are hanging wires. I mean, they have to be because, I mean, they are not contracted. They should not be contracted. No, I don't need any question.
All right, well, that's yeah, maybe it's not a good question, but let's bring this question. I haven't done that. So here you show that these two numbers could be used for their conserved quantities, and are they physical? I mean,
Well,
in a given circuit, are they something interesting? Like
yeah, I will show you in the slide what they give. Yes, they are physical. I mean, they are physical, well, in the sense that they give, let's say, local conserved charges, right, of this model. Like they would give you, in the throttle limit, they would give you Hamiltonian heat current, energy current, and all this fancy local operators which are exactly conserved in the Heisenberg model, for example. And in general, they give you conserved charges. But first, we have to okay, there are two kind of steps before that that we can argue why this gives you conserved charges. So first, I mean, okay, the reason why I'm kind of giving you this kind of presentation in this particular formulation is that it's kind of ultimately also discrete, so it can be applied immediately to kind of quantum information theoretic setups, but also, I mean, it generalizes basically the integral models in a sense. So basically, it of course gives back the standard, let's say, Hamiltonian integral models in the problem. So two more things I wanted to say.
Sorry, can I just ask?
Yeah.
In the spirit of this question, here now we connected these A spaces to physical 1 and 2 spaces. So we assumed all spaces are equally dimensional, right?
Yes, you will do that. Yes.
Okay. So in generally, this construction would not work if we have auxiliary spaces. It would not be feasible.
It will, but I cheated you a little bit. It will, but you have to use simply the most general solution of the more general solutions of the Yang-Baxter equation, where these three spaces are different, but then this object will not be the same as the propagator, because this object really has to intertwine two auxiliary spaces. So it could be the auxiliary space is something completely different, and I hope that I will be able to tell you something about that, because it's also very interesting in physics. I mean, when you take auxiliary space which is infinitely dimensional, right? You also have solutions in Yang-Baxter, which intertwine finite and infinite dimensional spaces. But in this case, this intertwining has to be infinitely dimensional quantities. It's not the gate anymore. There exists
the Yang-Baxter equation is not a gate. In this equation up there is different.
In this one, it is just a gate. In this one,
okay, in the proof we use something. Okay.
These two are then fundamentally different identities.
Yeah, this is what I meant. Okay.
They are both coming from Yang-Baxter, from, let's say, universal solution of the Baxter equation for the underlying symmetry of the problem, but they are different. They are different manifestations. They are different representations. Yeah.
Could you repeat for me why you write mu minus lambda in one of the use for lambda minus lambda?
Because this is unitarity, because the composition of tau minus tau should be, minus tau is tau inverse, right? This is the gate where tau is the time, and this is minus time. If you compose gate with time and minus time, you get 0. Putting minus t to the argument gives an inverse, right? That's something maybe I haven't expressed yet, but if I, this is just. Okay, sorry, yeah, it's, of course, it's important to clarify that. On the other hand, we don't want to get too much into detail here. But two things I wanted to still say. One is kind of a nice, I mean, I already told you how to, I already told you that this is basically, that's the main physics, right? That you have some analytic family of operators which computes with your time evolution. But even more is true. This time evolution can be actually completely formulated in terms of this operator. So there is this identity, which I will leave you to prove as an exercise for those who might get some passion in this. There is a nice identity which tells you that u is just t of minus tau over 2 to the inverse times t of tau. So if you just take a transfer matrix of a parameter of particular transfer matrix in the free parameter lambda, which need nothing to do with the total time, but if you put the parameter as half of total time here, and inverse half of total time minus half total time here, and then put the inverse on the transfer matrix and then compose the two, magically this becomes just a propagator. So again, there is a proof of that. So proof is an exercise. And it needs only an extra, nothing else. Well, what you need also is that R of 0 is a permutation. U of 0 is a permutation. Because you see then, I mean, in this transfer matrix, you have lambda plus tau over 2 and lambda minus tau over 2. If you put lambda tau over 2, then there will be zeros. There will be zeros in the arguments of R matrix, and then you have to use the fact that whenever you put 0, you have pure permutation. These permutations have momentum, it just shifts things around. And this allows to make simplifications, and these simplifications result in this nice magic formula. So what is this formula? This formula is basically just the discrete analog of the fundamental relation of integrability, which tells you that Hamiltonian is the logarithmic derivative of the transfer matrix. This is just discrete logarithmic derivative. Right? Small tau is just like the difference, and this is the inverse. Logarithmic derivative is just 1 over t dt. Right? So that's okay. That's one nice thing. And the other nice thing is, of course, the charges that you can compute. Now there are conserved charges. So you can write operators which you can call q plus minus n, which will be derivative with respect to lambda of the logarithm of t of, sorry, there's this logarithm of t of lambda, and these are derivatives of order n, arbitrary order, at lambda, which is plus or minus tau. And now, I mean, of course, there are many things I have to leave in the air here, and the second thing I leave in the air is to show that these are exactly sums of local densities. It turns out that these guys are sums of local densities. So we can write them as some Qm, which are supported around J, and have basically support of size n. Well, n is not exactly this, so support maybe is size n, the way I'm writing this is n plus 2. So first derivative has support 3, second has support. So it's something like that. But the point is, these are finitely supported operators which only support on two sides, and then there's a sum. So just for illustration, I give you the yeah, maybe we can switch on. Okay, and then make space for next. Okay, so now that's for the XXX chain, so for the same model that was our main example. So now here I use slightly different notation. I just denote, for example, the indices in which this is act non-trivially, but you see this is the first charge, which I call P1, which is a combination of dot products and mixed products, right? It's manifestly SO3 invariant, as it has to be, but it looks like an energy. It looks like a Heisenberg. And that actually is, yeah, now delta for me is tau, so sorry for the change of notation, it's like a different notation. Delta is tau, but that's what it is, right? So, so you see, I mean, things get immediately very complicated. I mean, just to show you that, if you look at the second charge is Q2, Q2 already involves products of 5 different sites, operators which are kind of interesting symmetric combinations of 5 vectors, 5 Pauli vectors. Okay, so right, so now I'll just maybe leave that slide on because I just now have something related, which I will only sketch. So what else can we do? I mean, the question is, of course, can we do something interesting with these integrability structures from quantum circuits? Well, I mean, we can try to diagonalize the problem, right? We can try to find the eigenstates and the spectra of these evolution operators. We can use the ansatz. We could also done that. But then you may be interested really in fundamental kind of properties of dynamics, large integrable systems. For example, what happens to correlation functions of large integrable systems. And this turns out to be still a very difficult problem. So it's embarrassingly enough, I mean, having these nice structures still doesn't teach us much about asymptotics of correlation functions, time-dependent correlation functions. So if you're interested in magnetization dynamics of Heisenberg chains, this is still a very, very, very interesting scientific problem. They are quite unusual. I could give a whole lecture about that, but I decided not to. But maybe Larry will say something about this. But in any case, I mean, these are potentially very interesting kind of systems, in particular because they are exotic. I mean, it turns out that integrability changes physics. I mean, integrability makes physics different. It's not that integrability is just a tool to solve the problem. It's also a physical feature of the problem, and which we don't really yet fully understand, to be honest. So, I mean, to what is really the effect of integrability on transport, for example, spin optimization transport. So these are really interesting two questions which we are still working on. What can be said, but even more can be still asked. So it's something for the future. But one thing which is also interesting and follows from integrability are some other tricks which also teaches us about transport of this problem. So there are physics problems, physics questions which can be answered. And these are related to ballistic transport. So there is one nice paradigm that one can explore, which is dissipative boundary-driven open integrable circuits. So that's the third part of the first lecture. So dissipative open integrable circuits. And of course, I could tell a few things about this, but I will decided to tell you one subset about one subset of this type of problems, which are the boundary-driven circuits. Boundary driving. And more general, I think, study also circuits which have dissipation in the bulk, dephasing, and also they could be mapped to integral systems. But let's say as a teaser, I will just give you like 5–10 minute introduction to boundary-driven quantum circuits. So what would that mean? I mean, you could think of this as a kind of theoretician's game, right? You can write a problem which has a nice solution, and from this solution introduce some interesting physics of the problem. That's an example of that. So, what you would consider here is time evolution of the density matrix. So you write the density matrix in discrete time as some linear evolution law. It's like very close to this bacteria growth process that Tomaž was talking about. Now we are interested in completely coherent evolution, so we will not make any time-dependent noise. We just describe it as an honest quantum master equation with all the terms. But still, the fact that this is a dissipative system will help us a lot. Can help us a lot. So what we'll do now, we'll still do the same trick as before. We'll split this circuit into two layers, even and not, so the bulk of the circuit will be exactly the same as before. So this M will be split as M odd times M even. And what will be the action of M even? Action of M even on the density matrix will be sum over some operators. So first I will apply Schrödinger picture evolution on the density matrix. Okay, that's just, remember what it is. This is just the tensor product of the gates, right? Non-interacting gates. But on top of that, I will also put what people call Krauss operators. And Krauss operators that should act on the rightmost end of the system. And there could be, let's say, a couple of those, let's say 2. And then I will put similar for the odd layer, and I will make a picture again, because as I claim all the time, pictures are much more than formulas. Picture will be here. So then again, what is, for me, what will be the U even? I will just remind you, will be U12, U34, and now this is just with this new notation, but this is a tensor product, right? Now, what I will change now is I will take L off, not even, because I have an extra side, I have a boundary, so it's convenient to take L off. So if I look at pairs, I stop at L-1, and then at the very last M, I can put some boundary to it. So this is the L side, okay? This is the right end, but I denote it as L, so for the confusing notation, right? This is the right end. And then I take the odd part, and the odd part will be starting with magnetic field to the left, and the first thing, affecting the first thing. So this is the magnetic field in the z direction, and then 3, 5, and up to the last, which is okay. And then I take some two Krauss operators. Well, it doesn't matter so much what they look like, but for completeness, I will apply them. So thing 1 left, which is there are some parameters. On the left, there's 1 plus, and on the right hand, first would be 1 as, I will explain later briefly what these operators do, but so these are usually associated to dissipative processes in physics. They still maintain all the physical properties of density matrix, but they provide either some sort of strong measurements or dissipative processes in general and so on and so forth. And as an effect, they provide driving of the system because they only act on the boundary size of the system, so they provide non-equilibrium state with potentially spin currents in steady state. So remember, there were 4 parameters here which were related to driving. There were 2 fields, and there were 2 gammas. So remember, these gammas were here. And if you finished writing the formula, these gammas, I mean, these are basically, this is the last guy, okay? So these are the more important processes. These are the, we call them amplitude, damping and raising of processes, right, which lower and raise the spin, so they basically inject or absorb magnetization in the system. And so they are responsible for spin transfer, because they are opening the system and providing exchange of magnetization with the environment. And so this could be kind of understood as interference driving, and these magnetic fields in the boundaries could be considered as interference driving. So it is 4 sources.
I think there is a typo in K1R. So K1R acts only on sigma LZ, right? So that's the first one should be. Yes.
Okay, so now how do we imagine this now? We now imagine it as one layer of circuit where I will now just use 7 sites as an example. And then I will use this R. Now, but these guys act on density matrix, so they act on the left and on the right copy of the density matrix, on the right of the cap. So what I have to do now is I have to take 2 copies, right? So to stress that there are 2 copies, I will put double wires, okay? So this means like a folding, right? It means like I have 1 on the top and 1 on the bottom. This is density matrix. This is 1 and 1 bar, 2 and 2 bars, okay? L bar. Bar means the second, I mean the bra, let's say, the cat in the bra of the density matrix, right? Which you can consider the state of two states. Again, this is the same vectorization that the Professor Tomaž so it's a very, very important trick in quantum physics. Before you use all the time. Okay, and then this would be the way that this even acts. And the only coupling between the 2 copies, right? This would be completely different. The only coupling, so you can think of this to be doubled, right? This is all doubled, so 1 is before, 1 is behind. And the only thing that is coupling between the 2 replicas is this guy here. Is this index L, which is somewhere over here. This index that is somewhere over here basically is the only thing which reminds us that this is a non-unitary process. Otherwise, this would be a non-unitary process. A unitary process means that it acts independently on the forward and backward fluid, on the prime decay of the density. But this only acts on the boundary, okay? And now this will be the first part, and this will be the second part. We just shift, right? Shift by 1, so if you go by, I didn't write 2, 3, 4, 5, and so on. And now this guy. Now this is K, this is K right. This is down, this is down, this is down. If you want behind, there is minus tau behind. There's a reminder, this box behind has minus tau argument, and then there is the left. Okay. So that's the diagrammatic representation of the full Markov chain. So this is what sometimes could be referred to as a quantum Markov chain. This is a propagator of the quantum Markov chain. Right? It's a master equation, right? For the Krauss form, that's the whole area. And so what you might be interested in, and I will just tell you this, nothing else, but you might be interested in the steady state. So you may refer to it as life. So you may call it rho infinity because it is a limit, it's a fixed point of this process. If it's unique, it's a unique fixed point of this process, and usually it's unique. With the operators I gave you, you can prove it's unique. So this is basically a fixed point. And the reason why I'm telling about this is that it's again integrability trick that allows you to write this operator explicitly and proving that it's a fixed point only using the Young-Master equation. So there's an ansatz. I mean, sorry, I have to go very quickly here because it's not the point to go into any detail. I don't use too much time, but still, I mean, since there is lots of physics coming out of this, I still decided to tell you a little bit about this. So, and it's kind of similar to what I did before, so I can basically rely on you having already absorbed a little bit of the same material. So the ansatz, the fundamental ansatz for this fixed point is the following. It's quite intuitive. You write it as a, what I would, well, if you want, you can think of a density matrix as being manifestly positive, and to look manifestly positive, you can write it as a product of two operators, one of them being dimensional adjoint of each other. So that's really something that you can show that it's always positive semi-definite. And then to make a trace one, you can normalize the trace. So this you can think of some sort of non-equilibrium partition function, but the structure is basically reminds you that you are doing quantum mechanics because it is like probability and it is like the amplitude. So you write it in terms of what we call amplitude operator, and this amplitude operator is an MPO. Is an MPO. And it has exactly the same, well, almost the same toolbox that we use to write transfer matrix of an integral site. So, but I will use slightly different symbols to stress that now the two spaces are not equal. So now I have two spaces, one I call auxiliary, the other I call physical. So this I call now Lux operator. So this guy is in auxiliary space. This is a Heisenberg state or ground state or whatever you want to call it. It's the first state of a ladder of states in auxiliary space. And this guy acts in two spaces, auxiliary and physical. And this guy has an explicit form for the Heisenberg model. I will sketch it. It has basically, it has two feet, one in auxiliary, one in physical space. You can think of it as a 2x2 matrix in physical space of elements which themselves are operators acting in auxiliary space. So this guy is acting on auxiliary space if you want. And these guys, S, Z, plus, minus, they form a representation of SU2. But it's a very special representation of SU2. It's not a unitary representation. It doesn't give you the. It's an irreducible representation, but it's infinite dimensional because it corresponds to a complex spin. It corresponds to a spin parameter is S, which is a complex number. S is not half integer. Okay, so now, and how do you see that? Well,
wait a second. So the last operator acts on the second to last site,
yes,
or
the last operator acts on the second to last.
what happens with the last?
What happened to the last? The point on the last, yes, I forgot to put the last. So. It's staggered product. It's a product where each other spectral parameter shifts by tau. The same as before, but now I decided to write lambda, lambda minus tau, lambda, lambda minus tau, rather than lambda plus lambda minus. So it's just a definition of what I mean by lambda.
So the third one is still going to be just lambda, right? Let's say, for instance,
Yes.
okay.
It's a staggered product.
Mhm.
Now the point is I have two free parameters in this ansatz. One is lambda, and the other is s. They are both complex numbers. And these two free parameters can be set by 4 parameters in this game, which are 2 gammas, which are both real, and 2 b's, which are both real. So there is a one-to-one mapping. It's very explicit. I will not write it down because time is precious, but you can find it in our papers. But there is this nice correspondence between these two complex parameters. One you can call spectral parameter, and the other you can call representation parameter. They are both arbitrary complex numbers, and they are in one-to-one correspondence between with 2 external fields, 2 coherent driving parameters, and 2 external dissipation parameters, which are incoherent parameters. Okay, and well, and then again, what you can, how you can, I mean, how this is, I wrote many formulas, and I promised you that I will not cover the formulas. I will just sketch a picture which gives us exactly the same thing, right? So what is our density matrix? Our density matrix basically is a staggered transfer matrix. Right? No, now it's 1, 2, 3, 4, 5. That's right. Yes, we want, right? It starts at state 0 and state 0. Now, let me put this guy away. Because it's fundamentally different. This one has infinite dimension. And then okay, and now these are Lax operators. These are Lax operators lambda, lambda minus tau, lambda minus tau, lambda. And these are the L-level operators, lambda, lambda minus tau, lambda minus tau, lambda. And this is the product, right? So this would be our omega, and this would be our omega dagger, right? It's omega dagger omega, right? And to show stationarity, it's probably already ambitious, but still let me stress now this guy is infinite dimensional. So why I'm stressing this infinite dimensionality so much? Because if you look at this as an NPO, right, people who do tensor networks for living, right, they would do this numerically. They would try to approximate these states numerically. But they have a hard job to do that here because they need high bond dimension, right? I mean, these guys are raising and lowering operators in the auxiliary space. So if you want to climb, if you have a large system that's 200 sites, you want to climb up to 200th level, right? I mean, there's a level operators, and you have to go up to, let's say, 100, so that you can come back to 0. Right? You start from 0. There is this S plus minus in auxiliary space are level operators in this here. It's a highest rate here, or lowest rate if you want. This is lowest rate state. But there is no highest rate. It's infinite, because spin is complex. It's not half integer, it's aerodynamics. So, the reason, I mean, very important physical consequence is then that the entropy of this state, the operator entropy of this state is not bounded. It can grow logarithmically. It's like a critical system. You can grow, well, not linearly, but logarithmically, because number of states grows linearly when the system starts. You need to support this. So it's not so easy. It's not so easy to approximate numerically. Yet, you know, we have a manifest analytical formula. And how do you prove that it's a fixed point? Well, again, you need some sort of intertwiner, right? Basically, you want to apply, what you want to do is you want to apply, I will just do it for a sketch. What you want to do is you apply here, well, how to do it? U and U dagger, right? I erased already, but there was a U and U dagger on each side, right? So you take a density matrix, you apply U dagger, so here is tau minus tau. So then I look at these guys and I use again the Baxter equation to pull the Q and then I annihilate. There's one more thing which I completely neglected, but if you are careful, you need some diagonal operators here. operators. This is physical space, so there are 2 by 2 operators. You just have to do with the left-right asymmetry or chirality. This problem might have left-right asymmetry. And if it's left-right asymmetric, you need also some diagonal operators here. These diagonal operators are totally benign because they are this gate is invariant and tensor product of 2 diagonal operators. So the fact is that this can be unclear. So in the bulk, everything can work. This is a steady state, right? You do it first in one line and then the other line. And then the more kind of subtle thing, the more important step is the boundary. When you want to when you want to apply the boundary, when you want to show that the boundary is consistent, right? I mean, this will then fix you these 2 parameters. Right? So when you have a function lambda and s, which is a function of gamma left, gamma right, b left. Okay. So now I want to stop because I want to keep at least half of today's lecture ready for chaotic circuits. But I just want to show you some slides here. Now, it's a good idea to use slides. So what happens now if you do this and compute observables? This is actually for the trotterized case, which was done earlier. But the solution is more general, but it of course also absorbs the total limit. But just to show you that physics can be very interesting and inspiring, just deduced from this exact solution. Then if you look at, then you can compute observables, right? Once you have this MPO, we haven't discussed it, but that could be a separate lecture, right? How to compute observables. But once you have an MPO, I mean, people already start in classical stochastic systems like exclusion processes, I mean, develop technology how to compute observables. The technology here is very similar. It's very efficient. Once you have local observables, you just define some sort of transfer matrix which acts in this direction, and then computing observables is just action of a 1D transfer matrix. It's like 1D easy form. It's not more hard. Right? Well, this auxiliary space is infinite, so yeah, it's a bit tricky, but yeah.
I mean, I maybe have a very stupid physical question, but would you remind why those pumps do not simply heat the system to infinite temperature and will have unit density metrics?
Well, why what? Why? Because of boundaries, right? I mean, these boundaries try to pull up. These boundaries are actually frustrating, right? I mean, they want to polarize in different directions. This one wants to polarize up. This one wants to polarize.
So it just kind of pump energy through the system. It's
a spin pump, right? It's a spin pump. It's a source and sink of monetization, right?
Yes.
And both have finite strength, so they compete. So inside there has to be, well, this is what it is, right? Now, what you can compute is the average. So, you can compute the spin profile, right? And then you see that spin profile, and then depending on the, well, I didn't define this parameter, but this parameter. Now, what I'm doing now is I go beyond isotropic Heisenberg and define anisotropy. If you define anisotropy, you can define anisotropy also for the gate model, but you can, here this is just a single parameter in the gate model. There are 2 free parameters, but yet still there is a combination which represents anisotropy. So if anisotropy is equal to 1, this is isotropic model, this is exactly the model we discussed, then you get these cosine shaped profiles, right? So it's not Ohm's law, right? If you want Ohm's law would be, or Fick's law for spin, would be linear profile. No, this is not, it's cosine profile. And then if you look at the current, the spin current, as a function of system size. So here L is N, so N is the system size. If you look at, again, this blue is the isotropic case. If you look at the isotropic case, this is log. You see that in case like power law, but not power 1 as you expect for Fick's law, but power 2. So it's an exotic state, which is subdiffusing. Actually, this has been, I think it's also been seen roughly in this visibility experiment. I mean, roughly, it's not very accurate in the experiment, but still qualitatively, I think it agrees with what people have seen in the recent paper in Nature. And yeah, I mean, what is kind of remarkable, yeah, this is an exotic state, which is highly coherent, I mean, highly correlated, right? So the question is, does it entail some interesting physics? Well, yeah, you can simulate it, you can check it. But that is maybe more interesting to the Gibbs outside isotropic point, if you go away from isotropic point, if you go to the so-called easy axis regime, delta larger than 1, then you get like a spin insulator. You basically have a spin profile which is 2 domain walls, and the spin current is exponentially small. This is exponentially small. It's exponential system size. And if you are in the easy plane regime, delta less than 1, then the transport is ballistic, the profiles are flat, and the current doesn't decay in system size. And you can go further, I mean, okay, you can compute also 2-point functions, right? 2-point functions, again, you can compute them analytically. You find a result which is kind of curious. We still haven't completely understood what it means, but it's actually interesting because it has a part which is exactly the same as people find in the classical exclusion processes, the so-called hydrodynamic correlator. Right? It goes like 1 over L or 1 over N in this notation, times the product of the two variables, psi1 and psi2 are two state variables, x over N or x over L, and y over L. Now, two spins are positioned somewhere, but this problem is not translation invariant, so its correlation happens to function of both parameters, both variables. But then there is this trigonometric factor, which is curious. And most interesting, if you look at a steady state density matrix of the easy axis, easy plane case, then from it you can deduce a new conserved charge, a new conservation law, which is not local but is quasi-local, and this can give you bounds on the spin transport in ballistic. So it can give you bounds on ballistic spin transport at high temperature. I mean, this has been already, more almost 12, 15, 30 years ago, right? But still, it's kind of, I mean, still not people, not everyone is completely happy with this interpretation. I mean, why is not so kind of straightforward? Because it predicts this Mazur bound, and then you can use this conserved charge in Mazur bounds for the spin ballistic contribution to spin transport, and you find that it's a fractal function of the anisotropy. So you find that it is not a smooth function. There's nowhere a smooth function of anisotropy. So it's there has been a last progress on this question was using generalized hydrodynamics and thermodynamic ansatz by Eme and Jacopo, and they have completely confirmed this kind of bound. So they have basically shown that this bound is saturated, and it is still a fractal even at finite temperature. So this bound has been derived by myself for infinite temperature, but Eme and Jacopo have extended it to finite temperature and show that it's also a fractal, nowhere continuous function of a bound. So I mean that's just physics, which is weakly connected to what I've said in my lecture, but just to give you motivation why this could be interesting physics. Now here, why you should raise your eyebrows? I mean, because I'm telling you that the condensed matter system has physical properties which are discontinuous functions of parameter in thermodynamic. This is not a phase transition. Well, you can think of it as a kind of phase transition, but it's not a standard phase transition. It's just instability of physics in thermodynamic. And there is no theory which would prevent that, even though people find it very strange. Okay, so and then, yeah, this has also been actually, well, now the question is, could this be seen on a quantum computer? This model actually has been simulated again by Google's group, but they have not looked into that. They just look at bound states of quasi-particles for this model. But with Marco Lubotin and Leonard Zadnik, we have actually looked also into the Drude weight of this discretized model. So now we go really to a discretized model, anisotropic discretized model, and we find, well, again, here these fractal Drude weights, different dynamic exponents depending on the different levels of anisotropy. It's either ballistic or insulating or diffusing if you want, or super-diffusing, right, which is the isotropic. Yeah, this is something maybe that Leo will often tell you something more about. So, okay, so this will be the end of my first lecture. Sorry, I've been a bit longer, so I have to speed up with my second and third lectures. But is there any question before I switch gears? Yeah.
People also work on some boundary monitor system.
Sorry.
People also work on some boundary measurement, not class operator.
Boundary measurement.
Yes.
So
without summing up class operator, one class operator and to denormalization.
Just one class operator.
Yes. And to denormalization.
I don't know.
It's also.
I don't know. I mean, you can think of strong measurement as in terms of Klaus operators. So it's exactly the same thing. So, But I'm not sure. I mean, maybe we can discuss later. Can get deeper into this. Okay. So let me now turn off the slides and go to question number 2. If there are any other questions, I'll write it down. Please. Stop me. Slides.
I have a question.
Yeah.
Will these integrable circuits thermalize to some GGE type of thing?
GGE, yes. Yeah.
Is there a proof of it?
Probably, huh?
Is there a proof of it?
Well, there is not even a proof that state will thermalize to GGE in Hamiltonian setting, right? I mean, it's
No, but
it's what everybody assumes.
In this 4K or in this discrete setting, can you say anything like this? Or?
I think you can. I think we will have discussed this flow GGEs and well, combining with integrability. And yes, I think the prediction is very clear. Also, there is TPA, so you can understand GHD for this model. It has been done to some extent. I'm not sure to what. I mean, actually, we had recently a paper on the chiral version of this model, also looking to GG. So you can think of. There is a very easy way to make it chiral. Just you think of every other space being different. Right now it's spin 1/2, spin 1/2, spin 1/2, spin 1/2. So you can think of spin 1, spin 1/2, spin 1, spin 1/2. There is also R matrix for that. There is R matrix for everything. I mean, as long as you have SU2 symmetry, right? You know, there are models which are kind of very, very strange, but they're still integrable and satisfying. I mean, they come from that. So you can think of these chiral circuits. Of course, they don't correspond to any Hamiltonian anymore. There is no throttle limit, but they define some sort of one-dimensional transport, which is integrable. It's studied. So that was a paper a few weeks ago by Lennart and myself, Marco. But okay, yeah, we can discuss more if you want. Okay, so now let me just really, as promised, tell you something about chaotic circuits, special class of chaotic circuits though. I mean, it's not very ambitious, and I will let to other lecturers to speak of more, let's say, generic or general chaotic systems, but as I announced in my motivation yesterday, I like to think of Baker maps and cat maps of chaotic unibody systems, so for that one has to sacrifice something, make things simpler, but not too simple, of course, and yeah, and there we are at lecture 2. And I will discuss dual unitary circuits. And in this lecture today, I will discuss exact dynamic manipulation functions. So I will split this into lectures. Today I will discuss dynamic manipulation functions. Tomorrow I will discuss spectral statistics. Okay, so we made already kind of introduction into tensor network notation, so I will not need to say much more. Let me just define what I mean by two-point correlator. So whenever you have a many-body system, extended many-body system, lattice or QFT, the fundamental object which you want to understand, which we tell you a little bit or a lot already on dynamic features of this problem, is the two-point dynamic correlation function. So you take two local operators, A and B local operators, which means they're They are living in a local Hilbert space. And then we define what I would call CAB or VA at position yx and t. Okay, so they depend on two coordinates, x and y, and on integer time and on choice of two operators. And this will be trace of b at position y. I already introduced this operation yesterday, right? When I put a Roman index, I mean now an embedded operator in the tensor product space. So I involve an operator A placed at site x for time t, and then I overlap it with operator B, and then I divide it by d to the L, right? D is the dimension, d to the L is the dimension of the space, right? So it's an infinite temperature curve. Why do I use infinite temperature? Because there is no sense to define temperature in flow persistence without conserved quantities, right? And by assumption, this model, well, as you can also verify later, but by assumption, by the preliminary assumption, this model will have no conserved quantities, so there's no reason to expect any meaningful time translation variant states other than the so-called threshold state, infinite temperature keep state. Okay, so now to give it a little bit more explicit, but then immediately I will write a diagram for that, and then we'll discuss the diagram. So that will be our u of t in x minus t. Okay. Now let me define slightly more sorry for being a bit over pedantic here, but I will define time evolution slightly differently. As yesterday, I will define time slices now such that the time period will be 2. So I will discriminate between having even an odd number of half-time slices, which you might do just to explore fully the lattice, right? So you can say, okay, u of 2t, this is just definition, okay? Is what I denoted as u to the t, and u of, remember, u was u odd times u even, and u to t plus 1, I will define as t times t times, so this u odd, u even to t times another odd. Okay, so it's in staggered product of u even, u odd times u even, and then since it ends at u even, you have another u odd.
So the dagger should be the left operator, and it doesn't matter.
Dagger should be on the left, yes, thank you. So now what we have seen yesterday is that if you do the diagram for a local operator now, you get an operator like this, right? I do it just schematically, right? And then you might get something which is already fully contracted, right? So now assume the system is large enough, so assume L is large enough, probably larger than 2t or something, or 4t, like 4t. So I will never hit the system's boundaries. And then what I will do now, I will place, so this is position x, and then I will place another operator in position y. So this is a ball, and now I put another ball here, and then I contract. And so what happens now is I can use exactly the same logic as yesterday, but now looking at operators which collide head-on here and here, right? So which means I can erase everything, which in this triangle, so this is the y. This triangle, and this triangle are completely freely colliding, and they can get annihilated. the same for this triangle. This triangle and this triangle here also get collided because I take their boundary conditions. And at the end of the day, I get that this is not a correlation function, of course, it's a y x t when it's contracted, right? And then this becomes an a. And then there are again these hooks. Right. Here is connections like this. Okay, I'll be more precise later, but I'll just give you kind of, just to check that you understand, right? I mean, please make sure you understand what I'm doing, right? If not, please, let's just. Okay, but now, of course, before continuing, it's now very, very useful to introduce formally the folded picture, so that now what we do, I will really fold this picture, so we'll put these two guys on top of each other. How do we do that without cheating? We should introduce kind of clearly slightly updated tensor network notation to accommodate for this. So try to use the board. Folded picture is the same as vectorization. So I introduce an operator space. Let's call it H op, local operator space, which is space of isomorphisms over Hilbert space, and which is isomorphic to tensor product of two local Hilbert spaces. So basically, it's just C to the D square. So what do I mean? I mean I'm using an operator, local operator, and I map it to a state. And in pictures, of course, we don't want to write all these lengthy formulas, but in pictures, what we do is we take an operator A, and in order to reduce the number of letters on the board, I will just put a bullet when I think of a non-trivial operator. And now this vectorization means I will simply put these two wires all up, so I could contract them and manipulate them together. So it's just that I just think of this second copy below, I can bring it back from behind. I make two sheets, let's say. I make two sheets, and one is the forward and one is the backward sheet, but they are together. They're just one on top of the other. And so then I will just use this notation here, if in order to be different, I might use a different thickness of the line, right? Saying this is now the folded notation operator. Operator is just now the wire which ends at the point. It's like a state. It's like a state because now it has a fixed single index. Single index, which is heavier, which goes over d square values rather than d. Okay, and now we have the operatorial gate. And now operatorial gate is basically a gate which acts on tensor product of two operatorial spaces. So you can think of two copies. U. Now let's at the moment be specific, so we take. So it turns out that it's better to put dagger on the top one, and yeah, because this one was this one was U, and this one was U dagger, U dagger. Okay, so it's better to put dagger on the top and U on the bottom. So this index is I prime, J prime, K prime, L prime. This is I, J, K, L. And then when we fold it, we go like this. And now this is I prime, J, J prime, K, K prime, L prime. These are double indices. And then we will just denote it as a single box, which we now denote as W, and we have thick wires sticking out of it. Okay, and now this thick index will now go from 0 to 3 for qubits, or 0 XYZ if you're on a value basis. And you can think of this representing this value in any operator basis you like, but in the beginning this is just bracket basis. So in bracket basis, this W formally is just this thing, right? You have a gate and then you take a tensor product between two replicas. These are two replicas forward backward. And then you take a tensor product of U transpose, because when you fold this guy, you transposed it, so it's U transposed cross U dagger. Okay, that's the most consistent way to do it. Okay? And then you repeat everything I've said for this gate. Now, you can define Heisenberg dynamics as dynamics which works in the space of operators, which you generate by a gate, which is now acting on 4-dimensional, it's a 4-dimensional local space, and you take operatorial dynamics, operatorial circuit. The only thing we have to be careful is that the order of even angles changes. I mean, when you do folding, you find that I mean, this has to do with the duality between Schrödinger and Heisenberg picture, right? When you take a composition of two operators, then the order is different when you go from Schrödinger to Heisenberg because of the So now again, the even will be this W and when this pi is again shift. Now very operatorial shifting the operatorial. Okay, so now after this we can write our fourth representation of correlation function. We can write exactly the same object as before. Now it's a big box where it says WT. Again, I have to define what I mean by W of T. W of T is W of W to T, and W of 2T plus 1 is W to T, but now I place W naught on the left side because, again, there is this duality between Schrödinger and Heisenberg picture, which means that I have to transpose when I go from one to the other. Please, whenever what I said sounds strange to you, please check it yourself. I don't have time to check all the little statements I make, but in order to make calculations consistent, you have to check these things. Now, yeah, and then what I will also have, what is also useful, is to represent identity in the quality picture. Identity operator. It's just straight wire, right? It's a delta from the delta. If I bend straight wire like this, I mean, when I go to for the picture, I just bend it like this, but then it's just like a thick wire and open circle. Okay? So it's a delta function, right? It's a state which gives you a delta function. If you want, it's a bell pair, right? Because now this guy goes to this guy, and they're just a pair. Okay? So under vectorization, identity matrix goes to a pair. So this is just a notation for the bell pair. And now,
for completeness, you should also mention that trace also goes to this empty circle, but on the other side.
Yeah, on the other side. Yeah. Okay, yes, indeed. Right. So also let's see. Right on the other side, we can also think of this. Yeah. And now this will be position y. Let's say as before, this will be position y, and this will represent operator b, and position x somewhere here would be operator a. And now these guys, again, will be unitary, right? Unitarity. How do I write unitarity of these gates, operatorial gates? Well, just think of this. When I contract these two indices and sum over, this is just U dagger, right? It should be identity, which means this should be equal to this k equal to k. It should be equal to constraining that k should be equal to k prime and k should be equal to k prime. So which means in terms of diagrams, if I put a circle here, which is like a trace because I just have to sum over, identify the Brian the cat, and sum over, so that's like a partial trace. It's a partial trace on this specific subspace. That's just one way of expressing unitarity. But unitarity has two manifestations, right? U dagger is identity and U dagger U is identity. So I can also do the other way. I can also identify these two indices. Then I get this, right? It's the same thing, right? Identifying these indices is then U dagger, it's identity, but that means identity that I should be the same as I prime and J should be the same as J prime, so that's the circles on the bottom. So this is unitarity. Actually, just to make a note here, this is like a footnote, not important for what I'm going to say next, but it's important in general. This relation seems to be, or not only seen, but they are more general than unitarity. They apply also when this gate is not strictly unitary channel. I mean, this is like, when you think of a unitary evolution, right, then if you fold it, this applies to operators, density operators, and then you can think of it as a channel, but it's a special channel which is called a unitary channel, and then it's called unitarity. But this could be a more general channel. This could be a quantum Markov channel, and this is a quantum Markov channel, and this is called unitarity because it just reserves identity. Apply to identity, it gives identity. Apply and preserve a trace. Taking a trace or the other way around. One is trace preservation, and one is unitarity. And for unitary channel, it's both called unitarity. I mean, it's both consequences of unitarity. Unitary channel, by the way, is unitary trace preservation. Okay, fine. So now I made a really unfortunate choice because these diagrams will use, but I have to now erase them. But anyway, so I think we are able to memorize this diagram. Right? There are two fundamental diagrams that we can use. But two more important are coming. Okay, so now let's do the. Now let's write this iteration function that I wrote somewhere behind. Now let's write it in terms of bricks, in terms of real bricks, operatorial bricks. So that the tensor vector operation function, explicit tensor vector operation function, of course I have to make a choice, so I make some choice, I mean it needs to choose, but I make a choice such that it will look kind of generic, typical. So this will be A, this will be B, and all the rest will be circles. And how do I get to this from that list that was like that? Well, you see, I mean, I had these guys on the top. I'm just sketching. I'm just sketching. So whenever I had a rectangle, because I started on a rectangle, then I use unitarity. Whenever I have two circles on the top, I can contract them. So I get circles here. Then I can still contract them. I'm only not able to contract as long as one is a different one. One is a defect, right? It's an operator. Then here I cannot contract anymore, so I can contract along the light rays, right? Now signals propagate with speed 1 here, so there is maximum speed, and this speed basically bounds, the causality, if you want, right? So correlation can only be contracted within this cone, right? The cone from the top and the cone from the bottom, right? These are the two cones, right? The forward and backward counter cones. And so correlation function is this rectangle, okay? So now, think of this, I mean, if you have heard some lectures in statistical mechanics, you should immediately see that this is very similar to standard models of statistical mechanics in 2D, the so-called vertex models. So these beasts here are like some weights, right? They are very strange weights because they are unitary matrices. Actually, if you write them in Pauli basis, they are just orthogonal matrices, but still they are kind of not positive. I mean, they could have positive and negative weights. So it's not exactly partition sum of an Ising model or vertex model, if you want, but it's very similar to that. I mean, formally, it looks like a partition sum. Right? So basically, what we have to do now is we have to sum over all the internal wires, right? Because this can take arbitrary 4 values, if you want, 4 qubits. So then it becomes like, if you want, 4 times 4 times 4 times 4, 256 vertex model, right? So each vertex depends on 4 to the 4 different values. In principle, of course, then it could be 0, but in principle, it could be all different from 0. So it's a very heavy 1 plus 1 or 2D vertex model. And we want to compute its partition sum. And this partition sum is called dynamical correlation function. It's an impossible problem in general. I mean, this vertex model will not be integrable in general. So what to do? Well, there's nothing we can do. I mean, it's one of the hard problems of many body physics is to compute time-dependent correlation functions. So that's, in general, there is no way to proceed. And let me just sketch one more thing. I mean, this is a rectangle, and roughly speaking, the sides of this rectangle are t plus x minus y and t minus x minus y. And right, so now what I mean by these guys, so to be precise, I'm slightly defining definition of circles, definition of circles. By slight definition, I will take this thing, of course, is just I prime, and that is I prime divided by square root of d. So I put this square root of d. I might put this square root of d everywhere. In order to avoid kind of overall normalization factors. But you may not like it, you may put explicit normalization factors in front of it. The problem is you have to normalize with a number of overall number of wires. Okay, right. So now, what can we do? Well, it turns out that maybe sometimes we can do something, and we can do something when we have special features. And what a nice special feature is when you have the circuits which are doing. So, I mean, the story to discussing these dual circuits was not very straightforward. It took us a while before we realized, what is the most elegant and simple formulation. So it started with discussing Ising model. So it's a model of a simple 1D Ising model with transverse and longitudinal fields. Thinking of these two fields as kicked, so time-dependent Ising model where magnetic field is switched on and off periodically. Then you can realize that sometimes, for some values of coupling parameters, J and transverse field, sometimes this Ising model has a very special feature, and it looks exactly like itself, even when space and time are flipped. In these circuits, but then of course I will not go into this route because it will take too much of time, but then you can generalize all this. You can think of Ising model and all models alike as brick-wall circuits, and equivalently, you can think of these circuits, by flipping space and time, thinking of time evolution going from left to right or right to left. Okay? So if you start from a gate again, this gate maps ij to kl. You can think of this also as mapping, let's say, ik to jl. So you can say ik to jl is the same as ij to kl. So you can define a gate which you call utilde. So in this case, utilde flips, utilde is a unitary matrix which propagates left to right. And it is related, matrix elements of utilde are related to matrix elements of U by simple swap of differences. Okay. So it's just swapping these two indices, for example. So that's basically equivalent to swap and partial transpose. So people in quantum information have actually looked into this. I mean, they call it index reshuffling. So it's, you know, this discussing these dual integer gates. I mean, it's not completely new in quantum information literature. What seems to be new is thinking of these gates as brickworks, as building blocks of extended quantum line systems, and studying those properties of those. Anyway, so right. So what does this buy you? Right? I mean, why is this so cool? Right? I mean, thinking of time evolution in this direction, of course, you know, and the fact that now, well, I mean, we just defined the time evolution in this direction, but what we are now asking is that both U, so dual unitarity, means that both U and U tilde are unitary. They are not the same. For Kick-teasing model, in the special point, in the self-dual point, as we call it, they are exactly the same model. So sometimes it can happen that the model is self-dual under this combination of partial transpose and swap. It's identical to itself. But in general, it is not required. What is required that both of these guys are unitary. So what do we mean by that? Well, I mean, if you just write it in terms of a normal gate, we can think of something like that. I'm sorry. You can think of U and U dagger, and now this is like I, J, K, L, this is K prime, L prime, I prime, J prime. And then you can think of contracting these two wires. Because you can think of, you know, this direction, so you can contract these two wires, and then what you want is to be unitary, right? So contracting these two wires means that this is going to be two empty lines, right? So this would be like K prime, I prime, and K I, and this should be equal to delta I prime, delta K prime. Now, immediately you can write this in terms of the folded gate, so this looks like a bit cumbersome, right? I mean, it's precisely the unitarity condition for the tilde, if you think for 20 seconds, but it, you know, it looks a bit kind of unnecessarily convoluted. So it's much more elegant if you think immediately to fold this guy up and write the same condition for W. The same condition for W, now these are thick wires, but the same condition for W means that now here you have to have a circle, and this has to be the same, so here you have to have a circle. So it's like a circle here and a circle there. And what I'm telling you now is that this should be a delta here, and delta, so delta here, and this after folding means you have a circle here, and here after folding means you have a circle there. So it's like a circle here and a circle there. And then of course there is a left-right rotated picture, right? Which can tell you that put circles here, and I have to get circles there. So we have like 4 diagrams. Let me now repeat these 4 diagrams. 4 rules of the game. The 2 are called unitarity, which I already had. So now we have much more rich set of rules. Now we can hope to contract much more complicated diagrams. So again, I remind you also why I bothered so much to tell you about integrability of circuits, because what we have now is just another kind of diagrammatic / algebraic technique to simplify things, right? Young-Baxter allowed us to do one thing, dual unitarity allows us to do slightly different thing, but you know, the idea is very similar, right? You invent a set of rules which allow you to simplify diagrams. Okay, so now immediately what you will see, I'm sorry I will have to finish soon today, but let me just, you know, bring us to the main point, and then we continue tomorrow from there. So now when we can do linearity, what we can do now is we can simplify this further, right? I claim, and of course, one other rule is that whenever you get a non-trivial operator colliding on a circle, this is 0, because this is just trace, this is A, this is just trace of A, which is 0. Well, I didn't tell you yet, but it makes much sense to assume that all operators that you will use are traceless, right? You can always split any operator into a traceful part times identity plus a traceless operator, and the identity is trivial, so you can leave it out. The identity just reduces the level of correlators by 1, so by assumption we can always study traceless operators, right? So whenever you have a traceless operator which collides on a circle, it's 0. Okay, so so what happens now? Let me just use this last few minutes to simplify this diagram, and then yeah, then I need to maybe to synthetate tomorrow my main statement which I will prove tomorrow. So I mean, this guy can be contracted by dual linearity, by rule number 3. This guy can be contracted by rule number 3. This guy can be contracted by rule number 3. This guy can be contracted by rule number 3. So unitarity, of course, has been already exercised, right? So now I'm using dual linearity. This rule will be, this guy can be contracted by rule number 4. This guy can be contracted by rule number 4. Aha! Now it's already, I mean, as soon as you disconnect the two pieces, right, you already know that things are trivial, right? Now these are trivial, right? Because now I can use unitarity to simplify this. This is 0. So as soon as you separate things into two separate diagrams, you know that things are 0. Okay, now the claim is that the only non-zero diagrams will be diagrams where you place two operators on the extreme opposite ends of 1D structure. So like this, only non-zero diagrams. So plane. Let's try to think about it, to prove it as an exercise until tomorrow. So only non-zero diagrams are diagrams which correspond to left or right sequence, or potential sequence. This cannot be contracted. Once you have this, there is no way to contract it. But that's very simple. That's a 1D vertex model, right? It's a 1D transfer matrix. You can compute a number. This is a number, right? There's no three ends, there's a number. But this number can be computed by multiplying the 1D transfer matrix. And that 1D transfer matrix actually is a very interesting object. It's just a quantum channel. Again, if you know something about quantum channels and quantum systems, that's a very familiar concept. Okay, yeah, so I think it's a good time maybe to stop here and discuss it further tomorrow. Any questions?